Hello, this is Mrs. Sharp, and today I'm going to do some video notes on concentration of solutions, specifically molarity. So this is all a part of Learning Target 9.1 still, where we're talking about just what are solutions, and today we're going to talk about how to express the concentration of those solutions. So these should go in your notes 9.1, and these should be going on notebook paper as opposed to a note packet. So you can just continue on from the notes you already have on solubility curves and the terms that we've introduced so far. So today we're going to talk about concentration of solutions, and what I have here is a picture of two beakers, and it says down here at the bottom that the two beakers contain the same number of moles of solute. So in this first beaker here we have 6 moles of solute. Let's say it's oxygen molecules. So fishies need oxygen to breathe in water, so the oxygen has to be dissolved in the water. So here we have a very small amount of water. Here we have the same number, 6 moles of oxygen, but there's more water. So that's a difference in concentration. And so it's the area in which those solute particles are either confined or spread out. So it tells you the number of moles per unit volume. Well, that's what we're talking about, concentration. Now, you are familiar with concentration just from things like making Kool-Aid. So if you make Kool-Aid and you add too much water, you don't have enough of your solute, which is the flavoring and the sugar. So it doesn't taste as good. Or if you don't add enough water, it's really sweet. So this is what we mean by concentration, and we're going to mathematically now be able to express what we mean by concentration. There's a few different ways you can do that we're going to talk about. The first is molarity. So these are the ways we're going to talk about. Concentration of solutions can be expressed by molarity, molality, and percent by mass and percent by volume. Now we're going to talk about each of these one at a time, and we're going to start with molarity. Okay, this is a definition of molarity. Molarity is equal to the number of moles of solute per liters of total solution. So go ahead and write that formula in your notes if you haven't already. Molarity is represented by a capital M. So big M is equal to the number of moles of solute per liters of solution. And remember, that means solution is solute plus the solvent together. So that total volume, and that's expressed in liters. So sometimes what you'll see is big M equals moles per liter, like that. So when we're thinking about our picture from before, something which has 6 moles in a small amount of space, they're still going to have the same number of moles, so that top part is going to be the same. 1, 2, 3, 4, 5, 6. So this top part would be 6 for both, but that bottom number would change. So if this is 1 liter, that would be called a 6 molar solution. 6 divided by 1 is 6. So a 6 molar solution. But if this was, let's say it's 2 liters, then 6 divided by 2, that would be a 3 molar solution. So you would show that as 3 and then a big M and call that a 3 molar. You'd say 3 molar, like your teeth, 3 molar solution. And that would be less concentrated than our first one, which was a 6 molar solution. Okay, so we still had the same number of moles in there. It's just showing us how confined or spread out they are. All right. So let's use this to do some calculations. So here's our first example. Make sure this goes in your notes. What is the molarity, so we want big M, of a solution of KOH made of 149.8 grams of solute dissolved in enough water so that the entire solution fills a volume of 687 milliliters? There's a couple of things that you need to know here when we get started. First, if we have moles per liter, if we're given grams like we are in the problem, like 149.8 grams, we have to turn grams into moles first. We can't do grams per liter, we have to do moles per liter. So we're going to need to do some of the conversions like we were doing yesterday. And also, we have 687 milliliters here, and a lot of times we're given milliliters, so 1 liter is equal to 1,000 milliliters. So anytime you're given milliliters, we're just going to divide that by 1,000 before it can go into our formula. Okay, so the first thing that we're going to do, I kind of lost my notes there up at the top, but that's okay. So the first thing that we want to do, remember we've got moles per liter, is I'm going to take those grams of solute, because it's moles of solute, so these grams, and I'm going to change that into moles of my solute, which is KOH. So I'm going to take 149.8 grams, and I need to turn that into moles. And in order to do that, I need that conversion factor, which is the molar mass of KOH. So I look at my periodic table, KOH would be 39.1, and there's only one of them, plus 16 for my oxygen, and then I'll switch colors so you can actually see this, and then hydrogen is going to be 1.01. And if I add those up all together, that's going to give me, whoops, it comes out to be 56.11 grams per mole. Okay, so I'm going to take this 149.8, and because grams is on the top, I actually need to flip-flop this conversion factor so that the 56.11 grams is on the bottom and 1 mole is on the top, and that's fine. And so I'm going to divide 149.8 divided by 56.11, and that's going to give me my moles of KOH as opposed to grams. And 2 decimal places is fine for now, so we're going to do I get 669, so I'm going to round up 2.67 moles. And then remember, big M is equal to our moles of solute divided by liters of solution. So now I know that it's 2.67 moles. And for our volume, I have 687 milliliters. Divide that by 1,000. If I divide that by 1,000, I'm just moving my decimal place 3 to the left. So 1, 2, 3. So I'm going to get 0.687 liters. And so now I'm just going to divide my answer, 2.67, by 0.687. And this comes out to be, again, 2 decimal places is fine. I get 3.886. So I'm going to make that 3.89. So this is a 3.89 molar solution. So what do we do here? 2 steps. We took our mass and we turned it into moles, and then we divided it by the number of liters, and we got our molarity. So it's a 3.89 molar solution. So this would be more concentrated than the 3 molar solution, but less concentrated than the 6 molar solution in this case. Okay, one more example here. Suppose you have 16.9 grams of NaF, so there's my solute. How many milliliters of solution would you need to make a 0.1 molar solution? So this time we have a little bit different setup. So our big M is still equal to moles of solute per liters of solution, but this time we already know big M and it's 0.1. We're also going to be able to find our moles because we're given grams of our solute, but we need to know this bottom part, these liters. So let's go ahead and change our grams to moles right now. So we have 16.9 grams of NaF, and Na is 22.99 plus F is 19. And I put that in my calculator and I am getting, what am I getting? I'm getting 41.99 grams per 1 mole. And so based on my conversion there, I actually need to flip-flop that. So I'm going to put 1 mole in the top and 41.99 grams in the bottom. And if I do all that, 16.9 is going to be divided by 41.99. I get 0.40 moles. Okay, so I know that 16.9 grams is a little less than half a mole. So now I'm going to take my formula and plug in what I know. So I'm going to clean this up a little bit, but you can still see it in your notes. So I've got M equals moles per liter. My big M, it says, is 0.1, so I'm just going to put 0.1 in there. My moles, we just said, is 0.40, and I need to solve for x liters. And so to do that, I'm going to multiply both sides by x. So now I have, I'm going to go up here, 0.1x equals 0.4. And then I'm going to divide each side by 0.1. And that's going to give me x equals 4. So this is going to be a 4 molar solution. So slightly, oh, excuse me. No, that's not right. I'm sorry. This is not molar. Why didn't you catch me and tell me I was doing this wrong? Haha. This is going to be 4 liters of solution. Okay. So 4 liters of solution then, 4 liters is going to be 4,000 milliliters. So I would need to dissolve that in 4,000 milliliters of solution.